Hello everyone. In this session, we will be demonstrating ETAP iDLS capabilities and how this solution addresses changing requirements on today's grid. We will begin by taking a look at some of the common electrical transformation challenges in today's grid. Next, we will take a general overview of what is the ETAP iDLS solution. And we will take a look at how ETAP iDLS approaches solutions for the industry challenges. Finally, we will end with unique solutions of how ETAP iDLS can be validated using a digital twin with ETAP. As today's grid evolves, there is a continuous transformation in today's grid that also requires a transformation in load shedding solutions. First, there is an ongoing transformation in today's grid with the introduction of new technologies and operations. One of the transformations is the increased utilization of renewable resources on the grid. Second, is the change in operation from a centralized generation model to a distributed generation operation scheme. These changes include in the mix both fossil and renewable energy resources at the transmission and distribution side, which makes the operation and reliability more complex. Independent system operators, ISOs, regional transmission operators, RTOs, and distribution companies must coordinate more than ever as generation conditions continuously change. As distribution companies perform load shedding at feeder levels, they will not only be dropping load, but generation as well. Distributed energy resource management systems must adjust to significant changes, and demand and operation is changing. These include changes in demand due to scheduled conditions or unscheduled conditions. Examples of these include unprecedented changes in load due to weather conditions or sudden failures or overloads of equipment. Now, given the transformation challenges we discussed earlier, this demands for specific requirements that a distributed load shedding system must adapt and evolve with the grid. These include understanding operating conditions at full visibility to determine load shed requirements at operating conditions. For this, visibility and understanding of the system is a must. Minimize impact on quality of service. As loads and feeders are being dropped, customer satisfaction drops. The system must be smart to minimize the impact. Protect against different contingency events. This means that the system must be on the lookout for contingencies caused by asset limits such as overloads, operational limits like power factor monitoring, schedule events like load forecasting changes, or unscheduled events such as unprecedented sudden demand increase caused by unaccounted factors. With DERs on the mix, power reserves must be calculated to minimize the impact on the system. Also, determining loads to drop must account for DERs as it will influence voltage support. Coordinate limits with ISOs and/or RTOs. Demand transaction limits between ISOs and RTOs must be accounted to make sure that unexpected demand in distribution do not affect the transmission side. Also, identify the location and disturbance and type must be unknown as well to make intelligent decisions. System must be complex enough to consider all the requirements yet make fast decisions over a large dispersed areas, yet ensuring system stability. ETAP offers the intelligent distributed load shedding system as a solution to today's requirements for load shedding. This solution is a model-driven controller system. It utilizes real-time operational digital twin to validate, optimize, predict, and manage distribution load shedding system, also known as load curtailment. The controller will take 4 core elements to calculate the best combination of loads to trip per event. First, it will calculate the digital twin model, which includes topology data and nominal data. Examples of this data include connectivity between feeders and generations, network capacity, and equipment limitations. Then, it will utilize real-time data to evaluate available loading and generation. By leveraging the connectivity from the digital twin model, the ETAP controller will evaluate how much generation is available, as well as reserves available during a contingency. The ETAP controller will also evaluate how much load is connected in real time. One key feature is that by using the digital twin model, engineers and operators will be able to create a digital twin model that can evaluate connected load to generation without requiring to write extensive logic or programming to consider all possible topology scenarios. Next, the system will consider load priorities to minimize impact of quality of service. Engineers and operators will be able to classify loads and priority per event or schedule. Examples of these include the capability to classify loads per service area, type of load, priority, and connected customers. Note that the ETAP controller can be configured to dynamically update these priorities as there are changes in generation, loading, or operating conditions. The final component will be the identification of system disturbances. This will indicate to the system all the events that it should be on the lookout that can destabilize the grid or require load shedding. User will be able to program the ETAP controller to identify events such as under-frequency trips, overload of equipment, critical levels in reserves, and unscheduled events, just to mention a few. With all these core components in the controller, it will dynamically evaluate and continuously predict the best combinations of loads to trip. This combination of loads will be targeted to minimize the load per event, which will minimize the impact in the grid while ensuring stability across the system. The ETAP iDLS controller uses a novel technique using digital twin models to perform load curtailment. It determines the minimum required load to shed based on the digital twin model, system topology, and real-time operational data. Then it selects the optimal combination of load to shed based on the type of trigger condition, load group priority, time of the day, and more. It has integrated options to minimize the impact on quality of supply, improving reliability indices. The digital twin model and load shed calculations account for distributed energy resources, DER. The ETAP iDLS is a critical component of the distributed energy resource management. ETAP iDLS is designed for geographical dispersed systems, such as transmission, distribution, and industrial dispersed systems. For the next sections, we will go and explain how ETAP iDLS approaches a solution for each requirement in today's distribution load shedding systems. The first requirement is understanding the operating conditions. As we discussed earlier, ETAP controller uses the digital twin to evaluate how the system is built and interconnected. The network topology processor is the main component for the digital twin to walk down the system and understand its topology. Note that the digital twin model is also the same model used during network analysis, therefore making the digital twin model the single source of truth. The network topology processor will walk down the digital twin to evaluate all available load and generation. As conditions in real time change, the processor will dynamically reevaluate the system topology, therefore recalculating and updating the available load and generation. Let's take a look at how engineers and operators visualize the digital twin model. The ETAP digital twin model offers different views to visualize the system connectivity. The feeder distribution views provides visualization of power flows between different areas of the network. Next, the visualization views include substation views, which provide one-line view of the power distribution, and geospatial view allows to visualize the digital twin as it is geographically arranged. Note that geospatial views covers the entire model distribution network. The iDLS controller uses switching devices modeled in the digital twin to evaluate how much generation and load is available in the existing model, eliminating the requirement of complex system and leveraging the existing digital twin already used for simulation. In addition to the digital twin model, ETAP also uses operator views where they can have summarized views of critical assets and measurements. Such views can include display of load schedules, state of available power for generation, and reserves, as well as critical alarms and conditions that need to be monitored, like under-frequency relays and overload alarms and other critical alarms for the field equipment. Interaction with existing DERMS is also possible all in one solution. This is very important in areas where voltage distortion and low voltage conditions can cause interruption of the internal processes. In this case, the load shed system must understand the voltage support that VERs can supply when performing load shedding. In addition to the digital twin model, the ETAP iDLS offers the operator views to facilitate the management and operation of the controller. Here's another example of another operator view displaying key summary data. On these views, operator can monitor the health of the system and takes action accordingly to maintain the reliability of the system. On the operator views, the system continuously updates critical data such as loading levels, frequency, current, voltages, and power factors. Other examples of summary views can be monitoring the state of feeders in a simple view per region. In addition to the summary views, users can also observe the health of other critical measurements at substation level, such as health of circuit breakers, under-frequency alarms, trip alarms, and control status. These views are not limited to electrical data, but also key indicators from other systems that can affect load shedding conditions. As shown in this example, the system is also monitoring the state of DERMS as changes in operation can affect load shedding conditions. In addition to the operator summary views, users can also view the state of the system from a geospatial view as shown in this example. Integration with DERMS using ETAP makes easier the operation and management of distribution systems. As shown in this example, user can add views for assets that impact the load shedding. In this example, we are looking at a system as part of the network that includes DERs that is interconnected in the network. In these views, the operators can monitor critical components such as transformers, voltage regulators, capacitors, and inverters. These views also improve coordination between DER dispatch and operating load. ETAP iDLS takes in consideration DERs as they can impact load shedding. For example, some of the volt-var optimization can operate in a conservation voltage reduction, which will require peak shaving to keep the DER stable. The next requirement for load shedding systems in today's grid is minimize quality of service impact. Many utilities define and track quality of service in different ways. In most, they track reliability indices derived from the number of interruptions and durations of interruptions. The load shedding system must also be able to minimize the number of customers interrupted and minimize the number of interruptions of each customer. The ETAP iDLS provides tools and capabilities to minimize the impact on quality of service. Dynamic load shedding priority is one of the tools. The iDLS allows you to classify customers and feeders such as critical, industrial, residentials, just to mention a few. Priority can be adjusted based on the type of customer. The iDLS also allows you to track total load connected and number of customers connected per feeder. This is very important when deciding the priority of feeders in the case that a large number of loads need to be dropped. As load shedding conditions happens, the iDLS keeps track of the number of trips that a particular load has been shed. It provides a dynamic priority algorithm that prevents that a single customer or group of customers to be dropped at the same time. With the readjust of load shedding priorities, the priority list is dynamically updated based on such algorithm to prevent repeating the same load. This functionality saves customers hundreds of thousands to millions in penalties due to low reliability or poor quality of service. ETAP iDLS controllers expands a digital twin model to use the Load Shed Configuration Manager tool. Using this tool, users can define the control philosophy for the distribution load shedding system. Users can select the loads that will participate as part of the load shed philosophy and organize the loads based on classification. Then, loads can be prioritized based on optimization group and classification, making the system intelligent enough to prioritize the best selection from a priority group and meeting the required load to shed. In addition, user can add administrative classifications to help better navigate loads participating in the control philosophy, such as location, substations, feeder names, among others. These priority groups are used as the primary classification to determine the loads that are the least critical on the system and trip from the least important to the most important. For example, in this classification, user can organize the list to identify the most important loads, such as hospitals or essential services, and ensure that they are the last resource to trip, and classify other resources, such as residential or commercial loads, that can be tripped without causing significant disruption. Information such as the number of customers connected and amount of power connected can be displayed here in order to minimize the disruption in a load shed event. The next requirement for today's distribution load shedding system is protection against different types of contingencies. For this requirement, using the ETAP Load Shed Configuration Manager, users can define all the possible contingencies that will require load shedding and its classification. Contingency events, also known as triggers, will be listed on this section. Examples of typical events configures are operational failures such as relay trips, grid and equipment capacity failures such as transformer or feeder overloads, and other type of contingency events. For example, with the integration of DERs, systems may be forced to reduce load because of sudden changes in available resources in generations, requiring the system to perform peak shaving and drop excess demand to keep the system stable. So in this location is where we are going to define all the possible contingencies that the system will be protecting. Using the ETAP Load Shed Configuration Manager, here we have an example of how different types of events are used to protect the stability of the system. Each event may be associated to a different response, while some events may require a different response level based on the severity of the contingency event or trigger. Trigger response can be selected as fast overload or scheduled. Based on the speed of the response required, this can be programmed accordingly, including operational delays. The logic configuration can help to further customize the load shed philosophy. This tool makes it easier for engineers with little to no programming experience to further customize the required load shed for each response, making etapiDLS a powerful controller to meet customized control philosophies. Users can create multiple logic schemes that can be designed to meet a specific contingency event. The schedule configuration tool additionally allows the user to match specific logic schemes to a contingency event or trigger that the system is protecting. User can make further changes in this view per event, such as the changes in priority after a load shedding event, definition of available power reserves, and final changes on the priority list for a specific contingency event or trigger. Users can create multiple schedules as priorities and logic can change with operating conditions. For example, priorities and logic can vary with operation, such as changes in time of the day, seasons, or unexpected events. So as we discussed on the previous demo, using the configure schedules, users can define schedules to take action on a specific event. Like on this example, we are showing how operators can create schedules for the system to take different action based on time of the day. Now, as we move into a larger scale, sometimes the schedules may vary depending on the day of the week, the day of the month, or seasons, or even a calendar date. Now, these schedules can be configured in a rotation calendar that can be adjusted to meet the operational changes in the network. Examples of these rotations can be changes on priority from daytime to nighttime load, or changes because of the seasons, holidays, just to mention a few examples. In this example, we can observe a schedule that is configured to change based on the time of the day. As hour progresses during the day, change as well. Then, as we see here, we have different rotation schedules that are saved to be used during a different time of the year. And then these daily schedules can be used on a yearly calendar to set different schedules to meet different changes in operation. For example, the rotation during the winter season changes considerably from winter, so users can specify different rotation schedules based on the time of the year. Part of the requirements of a distribution load shedding system is that it requires to provide fast coordinated response over large distribution areas. The etapiDLS controller can be programmed to communicate to multiple RTUs, which are going to be the substation devices executing the load shedding. As part of the configuration, the system will need to consider what RTUs will participate on the monitoring and load shed control for each contingency event. This is necessary as some of the events may be localized just for a single substation or substations and not global for the entire network, such as a feeder overload. Another aspect of the ETAP Intelligent Load Shed Controller is that it can work over a distributed environment. In this typical diagram, the ETAP Load Shed Controller operates in an environment where there is not only a master control center, but there is also a backup control center. Both servers work on a master and backup redundancy basis. So in the event of a failure, backup controller in the same site can pick up the operation, Or in the unlikely case where the communication to the entire master control center is down, the controller in the backup center picks up the operation right away. All this without the necessity to reconfigure the local substation controllers. Now, to summarize, we have covered how ETAP iDLS controller uses core data to evaluate the system to generate the best combination of loads to trip. Then the best combination of loads is distributed across the local substation RTUs. So as we discussed, the ETAP load sharing controller takes use of the digital twin model, real-time data, load priorities, and system disturbances to generate the combination of the best loads to trip. In order to understand how the ETAP controller calculates and interacts with the system, let's take a look at this operation. We will start with the ETAP load sharing controller, which will interact with the local substation RTUs. The local substation RTUs will feed the ETAP iDLS controller the operating conditions in real time. The controller will analyze the data, the digital twin, the load shed configuration, and optimization logic to produce the required load shed list per substation. The controller will generate a list of the predictive load shed tables, estimating the required load to shed for all contingency events given the current schedule, and send the data back to the substation controllers. At this point, the controller is armed with the necessary loads to shed in the event a contingency is true. Now, in the event where a contingency trigger is true, this can be because either the controller determines that load shedding is necessary or the operator needs to drop load from the network in order to keep the system stable. Each one of the controllers at the substation level will issue commands to trip loads locally, therefore ensuring that we have fast response over a large distributed control network. In addition to the load shedding configuration manager, users can visualize real-time monitoring and operation of the load shed schemes using the load shedding monitoring tool. Through this tool, users can visualize how much load ETAP is estimating for each contingency event using live data and the prediction of which loads will be required to shed in the case the event becomes true. Note that this tool also allows operator to arm or disarm protection for each contingency event. This is very useful because this allows operators to perform maintenance without having to worry about any false positive load shed events. Additionally, this tool allows operators to analyze the available generation and resources for each contingency event. Now, in this demo, we can see that the state of each one of the contingency triggers configured. It's showing the calculated available reserve, estimated load shed, and selection of which loads will be tripped in the case that the contingency event becomes true. Note that this data is also being updated in real time to the local substation controllers, keeping them always up to date. Also, in this tool, it can be analyzed the reserves available for each contingency event in real time. The reserves are considered on a system-wide basis to consider the available resources. This last is particularly useful when working with distributed energy resources. The communication view also displays the state of the communication for each one of the RTU controllers and their participation on each one of the contingency events they are protecting, allowing the operator to monitor all assets related to the load shed system in a summary view. Finally, the event section allows the operator and engineer to visualize past contingency events that were processed by the controller. In this view, operators can visualize any past event and all the loads that were selected to trip, the commands that were sent to trip, and any other equipment that tripped during this time frame. This tool is great to do post-event analysis, as there may be unscheduled events that require operators' attention. Another important aspect is the operator control for unexpected events. This is a necessary tool as distribution systems may require manual operator load shed in order to keep their system stable. There are many examples that may require the operator intervention. In today's grid, a good example this could be the result of unhealthy increase on demand caused by weather events such as a sudden freeze or a heat wave over a service area. In these situations, operators need to keep the system stable while dropping available load and protecting critical loads. In this example, we can see how an operator responds for unscheduled events and manually executes load shed in order to keep the system stable. The system will show automatically how many loads will be necessary to drop for this step to be executed. Once the command is executed, the signals are sent to the local substation controllers to execute load shed. Finally, we have discussed so far the integration and operation of an ETAP iDLS controller. And one last very important aspect is the capability to validate the control scheme using ETAP. Validation process starts by using ETAP Digital Twin platform for design and integration. Then the logic can be deployed to the controller, and it can also be simulated back using the ETAP Digital Twin design platform. This is typically done using a standalone environment before the controller is deployed. Once in operation, the digital twin model comes in full cycle for design, monitoring, and optimization by allowing users to simulate using real-time conditions, providing valuable feedback. The iDLS validation process is possible via the load shedding monitoring tool. Using this tool, users are allowed to immediately create simulations based on the results produced by the load shedding monitoring tool. For each contingency trigger that the ETAP iDLS controller is evaluating, users can quickly create simulations to validate using many of the simulation tools such as transient stability, low flow, and fault management and service restoration module. From here, simulation modules will be automatically pre-populated with the results from the load shedding monitoring tool to create a quick simulation. This will allow the system to be validated easily using the ETAP Digital Twin platform. In conclusion, today we have shown how ETAP iDLS solution addresses many of the challenges in today's grid transformation, including the requirements for system to consider different types of contingencies and also keeping in check with reliability indices with minimum impact. The ETAP Digital Twin platform provides a full-scale solution to design, operate, and validate distribution load shedding schemes. This solution is capable of being implemented over large areas of operation with distributed control. And finally, as one of the challenges from today's grid, we demonstrated how it can interact with networks that include distributed energy resources, which can affect the load shedding schemes considering their generation reserves and modes of operation. Now, let me address some of the common questions that we have received for the ETAP iDLS controller. First, is the controller compatible with a specific brand of RTUs, or does it require to use a specific ETAP RTU? The answer is, the ETAP iDLS controller can communicate with many brands of RTUs. The controller is capable of communicating using different communication protocols that are commonly handled in distribution systems, such as IEC104, IEC6150, DMP3, and ICCP to exchange data with other control centers. In other words, our controller is hardware agnostic, allowing to communicate with any RTU brand regardless of the manufacturer. Another question we commonly get is, how often does the controller recalculate the required load to shed? This is a process that will continuously happen between the ETAP iDLS controller and the substation RTUs. Our ETAP iDLS controller will be in constant communication with substation devices such as RTUs or other devices that provide continuous telemetry back to the ETAP iDLS controller. Then these changes are processed continuously back to the ETAP iDLS controller, which will evaluate the new operating conditions against the digital twin model and load shed control philosophy. Then the ETAP iDLS controller will send back an updated, predictive list of loads to shed back to the RTUs that have control over load shedding. This process will continue to occur almost every scan of the system, since it's more likely that on every scan there's always a change on generation or loading that will require the system to be reevaluated. And one last common question is, what are the general specifications of the ETAP iDLS controller? The ETAP iDLS controller is a substation-grade controller that can be installed through rough environments for operation. Typically, these controllers include fanless design, which can operate in extreme temperatures, typically handled in a substation, roughly between -25 to 70 Celsius. Typically offered within 512 GB storage. This hard drive size is typically enough to store the ETAP digital twin model and the load setting configuration. They are built-in rugged design to hold a typical substation conditions, which can be heavy vibration and dust. They are rack mountable, so they can be installed either in a substation panel or an enclosed rack.